In physics, gravitational waves are ripples in the curvature of space-time which propagate as waves, traveling outward from the source. Predicted in 1916 by Albert Einstein on the basis of his theory of general relativity. Gravitational waves theoretically transport energy as gravitational radiation. Sources of detectable gravitational waves could possibly include binary star systems composed of white dwarfs, neutron stars, or black holes. The existence of gravitational waves is a possible consequence of the Lorentz invariance of general relativity, since it brings the concept of a limiting speed of propagation of the physical interactions with it. Gravitational waves cannot exist in the Newtonian theory of gravitation, in which physical interactions propagate at infinite speed. Although gravitational radiation has not been directly detected, there is indirect evidence for its existence. For example, the 1993 Nobel Prize in Physics was awarded for measurements of the Hulse-Taylor binary system, which suggests that gravitational waves are more than a theoretical concept. Various gravitational wave detectors are currently under construction or are in operation, such as Advanced LIGO, which began observations in September 2015. On the 17th of March 2014, astronomers at the Harvard-Smithsonian Center for Astrophysics erroneously claimed that they had detected and produced the first direct image of gravitational waves across the primordial sky, within the cosmic microwave background, providing flawed evidence for inflation and the Big Bang. On the 19th of June 2014, lowered confidence in confirming the cosmic inflation findings was reported, and on the 19th of September 2014, a further reduction in confidence was reported. On the 30th of January 2015, even less confidence yet was reported. Nature went as far as publishing a news article entitled "Gravitational Waves Discovery Now Officially Dead." Introduction. In Einstein's theory of general relativity, gravity is treated as a phenomenon resulting from the curvature of space-time. This curvature is caused by the presence of mass. Generally, the more mass that is contained within a given volume of space, the greater the curvature of space-time will be at the boundary of this volume. As objects with mass move around in space-time, the curvature changes to reflect the changed locations of those objects. In certain circumstances, accelerating objects generate changes in this curvature, which propagate outwards at the speed of light in a wave-like manner. These propagating phenomena are known as gravitational waves. As a gravitational wave passes a distant observer, that observer will find space-time distorted by the effects of strain. Distances between free objects increase and decrease rhythmically as the wave passes, at a frequency corresponding to that of the wave. This occurs despite such free objects never being subjected to an unbalanced force. The magnitude of this effect decreases inversely with distance from the source. In spiraling binary neutron stars are predicted to be a powerful source of gravitational waves as they coalesce, due to the very large acceleration of their masses as they orbit close to one another. However, due to the astronomical distances to these sources, the effects when measured on Earth are predicted to be very small, having strains of less than 1 part in 1020. Scientists are attempting to demonstrate the existence of these waves with ever more sensitive detectors. The current most sensitive measurement is about 1 part in 7022499999999999999 times 1022 provided by the LIGO and Virgo observatories. The lack of detection in these observatories provides an upper limit on the frequency of such powerful sources. A space-based observatory, the Laser Interferometer Space Antenna, is currently under development by ESA. Gravitational waves should penetrate regions of space that electromagnetic waves cannot. It is hypothesized that they will be able to provide observers on Earth with information about black holes and other exotic objects in the distant universe. Such systems cannot be observed with more traditional means such as optical telescopes or radio telescopes. and so gravitational wave astronomy gives new insights into the working of the universe. In particular, gravitational waves could be of interest to cosmologists as they offer a possible way of observing the very early universe. This is not possible with conventional astronomy, since before recombination the universe was opaque to electromagnetic radiation. Precise measurements of gravitational waves will also allow scientists to test the general theory of relativity more thoroughly. In principle, gravitational waves could exist at any frequency. However, very low-frequency waves would be impossible to detect, and there is no credible source for detectable waves of very high frequency. Stephen W. Hawking and Werner Israel list different frequency bands for gravitational waves that could be plausibly detected, ranging from 10⁻⁷ Hz up to 1011 Hz. Effects of a passing gravitational wave. The effects of a passing gravitational wave can be visualized by imagining a perfectly flat region of space-time with a group of motionless test particles lying in a plane. As a gravitational wave passes through the particles along a line perpendicular to the plane of the particles, the particles will follow the distortion in spacetime, oscillating in a cruciform manner, as shown in the animations. The area enclosed by the test particles does not change and there is no motion along the direction of propagation. The oscillations depicted here in the animation are exaggerated for the purpose of discussion. In reality, a gravitational wave has a very small amplitude. However, they enable us to visualize the kind of oscillations associated with gravitational waves as produced, for example, by a pair of masses in a circular orbit. In this case, the amplitude of the gravitational wave is constant, but its plane of polarization changes or rotates at twice the orbital rate, and so the time-varying gravitational wave size exhibits a variation as shown in the animation. If the orbit is elliptical, then the gravitational wave's amplitude also varies with time according to Einstein's quadrupole formula. Like other waves, there are a few useful characteristics describing a gravitational wave. Amplitude, usually denoted h. This is the size of the wave, the fraction of stretching or squeezing in the animation. The amplitude shown here is roughly h equals 0.5. Gravitational waves passing through the Earth are many sextillion times weaker than this h10⁻20. Frequency, usually denoted f. This is the frequency with which the wave oscillates. Wavelength, usually denoted lambda. This is the distance along the wave between points of maximum stretch or squeeze. Speed, this is the speed at which a point on the wave travels. For gravitational waves with small amplitudes, this is equal to the speed of light c. The speed, wavelength, and frequency of a gravitational wave are related by the equation c equals lambda f, just like the equation for a light wave. For example, the animations shown here oscillate roughly once every 2 seconds. This would correspond to a frequency of 0.5 Hz, and a wavelength of about 600,000 kilometers, or 47 times the diameter of the Earth. In the above example, we actually assume something special about the wave, that it is linearly polarized, with a plus polarization, written h plus. Polarization of a gravitational wave is just like polarization of a light wave, except that the polarizations of a gravitational wave are at 45 degrees, as opposed to 90 degrees. In particular, if we had a cross-polarized gravitational wave, h times, the effect on the test particles would be basically the same, but rotated by 45 degrees, as shown in the second animation. Just as with light polarization, the polarizations of gravitational waves may also be expressed in terms of circularly polarized waves. Gravitational waves are polarized because of the nature of their sources. The polarization of a wave depends on the angle from the source, as we will see in the next section. Astrophysics and gravitational waves. During the past century, astronomy has been revolutionized by the use of new methods for observing the universe. Astronomical observations were originally made using visible light. Galileo Galilei pioneered the use of telescopes to enhance these observations. However, visible light is only a small portion of the electromagnetic spectrum, and not all objects in the distant universe shine strongly in this particular band. More useful information may be found, for example, in radio wavelengths. Using radio telescopes, astronomers have found pulsars, quasars, and other extreme objects that push the limits of our understanding of physics. Observations in the microwave band have opened our eyes to the faint imprints of the Big Bang, a discovery Stephen Hawking called the greatest discovery of the century, if not all time. Similar advances in observations using gamma rays, X-rays, ultraviolet light, and infrared light have also brought new insights to astronomy. As each of these regions of the spectrum has opened, new discoveries have been made that could not have been made otherwise. Astronomers hope that the same holds true of gravitational waves. Gravitational waves have two important and unique properties. First, there is no need for any type of matter to be present nearby in order for the waves to be generated by a binary system of uncharged black holes, which would emit no electromagnetic radiation. Second, gravitational waves can pass through any intervening matter without being scattered significantly, whereas light from distant stars may be blocked out by interstellar dust. For example, gravitational waves will pass through essentially unimpeded. These two features allow gravitational waves to carry information about astronomical phenomena never before observed by humans. The sources of gravitational waves described above are in the low-frequency end of the gravitational wave spectrum. An astrophysical source at the high-frequency end of the gravitational wave spectrum generates relic gravitational waves that are theorized to be faint imprints of the Big Bang, like the cosmic microwave background. At these high frequencies, it is potentially possible that the sources may be man-made, that is, gravitational waves generated and detected in the laboratory. Energy, momentum, and angular momentum carried by gravitational waves, waves familiar from other areas of physics such as water waves, sound waves, and electromagnetic waves, are able to carry energy, momentum, and angular momentum. By carrying these away from a source, waves are able to rob that source of its energy as well as its linear and angular momentum. Gravitational waves perform the same function. Thus, for example, a binary system loses angular momentum as the two orbiting objects spiral towards each other. The angular momentum is radiated away by gravitational waves. The waves can also carry off linear momentum, a possibility that has some interesting implications for astrophysics. After two supermassive black holes coalesce, emission of linear momentum can produce a kick with amplitude as large as 4,000 km per second. This is fast enough to eject the coalesced black hole completely from its host galaxy. Even if the kick is too small to eject the black hole completely, it can remove it temporarily from the nucleus of the galaxy, after which it will oscillate about the center, eventually coming to rest. A kicked black hole can also carry a star cluster with it, forming a hypercompact stellar system, or it may carry gas, allowing the recoiling black hole to appear temporarily as a naked quasar. The quasar SDSS-J092712, 65 plus 294,344.0 is believed to contain a recoiling supermassive black hole.